So let us look at how the operating system manages the free space. Now, instead of just having slots, you have chunks of memory that is not allocated. And you have a number of segments per process distributed all over the place, and each segment might be of a different size, right? So you have different memory that can be different areas of memory that can be used. Okay, the general problem that arises is that physical memory quickly becomes full of holes. Basically, you get like a couple of kilobytes here, 1 kilobyte here, 100 kilobytes there, 20 kilobytes here. Okay, so this is basically what we have been discussing, and we called already external fragmentation. Okay, if you get a new request for basically getting so suppose you have suppose that the first area not in use was 20 kbs, the second area was 1 kb, and the third area was 10 kbs, and you have a process that now wants 31 kbs for memory. Okay, how do you allocate that to that process? Okay, so one solution that people might think of is trying to do compaction or defragmentation, which was a very famous thing that you would do on hard disks back in the days. So you every now and then to make your computer faster, you needed to do defragmentation. This is no longer the case. So if you have been living through these days, when you needed to defragment your hard disk, there was one way to defragment the memory is to basically compact it this way, okay, by rearranging existing segments. This has a high overhead because you basically need to move all memory in, like, to start moving memory for all different processes, which is a really expensive operation, and that expensive operation would slow down your system. And since you can get these memory holes, this fragmentation quite often, that means that you can have multiple defragmentation runs every minute, which is really something that you do not want to do. So a better approach to manage this memory is using a free list. And this is basically the basis of memory management and memory allocation in most operating systems. Of course, you will end up with some external fragmentation at the end, but let us look how do you actually manage free space with memory lists. So segments make it easier to fit pieces into memory. So this is basically saying exactly what I just said. So let us look at an example. Suppose that this is your memory, how your memory looks like, and you actually want to allocate 15 bytes. How would you do that? That's an issue right now. So how the way that things are now, or one of the ways to solve this problem was basically through memory lists. When a process needs more heap space, it asks the operating system for more space using a call that is called mmap, memory map, basically. The OS will return more space as a pointer, okay, and this space will be added to the pool of memory that the process can work on. So now the process can call mmap get new heap space basically every now and then. So you sort of add to your heap space, and then you need to keep track, where is my heap space, okay, because it's fragmented over multiple segments. The process hands out small chunks of memory when calling malloc. So you do an mmap first to get some extra heap space, and then you call malloc that basically gives you small chunks of memory for your different processes. So you size of int or something. Malloc and free are provided by libc, so the operating system is not allocating space for object. It is more of a wholesale operation. So the malloc and free are actually what you do on the operating system mmap first. You call mmap first, so you get a whole lump sum of memory, large chunk. Okay, then you as a programmer, you use libc, okay, using malloc and free to basically allocate smaller chunks of memory within this heap that you just acquired. That way, the operating system is not actually allocating space for every single object every time you call, every time you actually need a size of int. You do not basically do that using malloc. Okay. Sorry, you do that using malloc, but you do not do that via the operating system. So the operating system does not need to manage basically small bits of memory for your program. Okay. Once you call malloc and get back an address, that address cannot be changed. That is now that is the address of the variable, no longer changeable. Okay, so libc cannot move objects. Once you get allocated a chunk in the heap using malloc, you cannot move it. On the other hand, Java runs on top of the Java virtual machine, which is actually sort of Java virtual machine is sort of a mini operating system that is running on top of the operating system that can do this fine-grained memory allocation, deallocation, movement, and fragmentation for a single Java program. So it's not across the whole memory. Okay, so an allocator, whatever that allocator is, needs to track what space is free. Okay, so you need to basically know that that, for example, in the previous example, that you have free space between 0 and 10 and free space between 20 and 30. And you do that using a linked list. Okay, so if you need 15 now, you can simply put like the first 10 bytes in the first free area, and then use the second 5 bytes, the rest of the bytes in the second free area. Okay, and change your linked list to actually basically say that, well, you know, I have only 5 bytes that starts from 25 to 30 that is free. Okay, so this is an example of how you would do that. So you take a free chunk of memory, allocate part of it, and leave the rest behind. For instance, if you do call malloc on 1 byte in this example, you can use the basically the address between 20 and 21. So in the beginning, your linked list looked like, okay, address 0 to len 10 was free, address 20 to len 10 was free. Now if you do malloc, then you'll actually start from now address 21 is free and len of 9 is free in the second chunk. Okay, so this is what happens.